Hi, everyone. I hope you're doing well. Today, we're going to finish up our discussion of quantum mechanics in one dimension. And we're going to talk about two topics. The first are expectation values, and the second are superposition states. Expectation values are, they're like average values in quantum mechanics. You know that quantum mechanics only gives us probabilities of obtaining different outcomes for a measurement. And we can't determine the outcome of any individual measurement. We only have probabilities. However, using those probabilities, we can predict expectation values. These are the average values that you might get by doing many measurements on a large number of identically prepared systems. That's an expectation value, and we'll learn how to deal with those in a moment. Superposition states are something quite different. We found that a system, like a bound particle system, has different quantized energy states, okay, different stationary states. And it might seem like those are the only possible configurations of the particle in that system. But it's not true, actually. Particles can also be in superpositions of more than one state. And the superposition states have some very interesting properties. Mainly, they evolve and change over time. Well, we'll come to both of those things in the course of the videos, so hang on. Okay, so here's our program. First, we're going to talk about expectation values, which we'll see are predicted average values of quantities that we might measure in a quantum system. Okay, and we'll use this, for example, to find the expectation value of the position of a particle in our simplest system, the infinite well. And we'll see how we can look at other quantities as well. For example, the expectation value of the potential energy in a simple harmonic oscillator. Okay? Under superposition states, we'll learn what these are. These are states that are superpositions of different energy states. And we'll look at that. We'll calculate the expectation value of position for a particle in a superposition state in an infinite well. To illustrate what's special about these. Okay? These are important topics. Our discussion will be a little bit mathematical, so hang on, okay? We're gonna have to do a couple of integrals as we work through these examples. And since I'm not so interested in doing integrals, I'm actually gonna write down a couple of results that we'll use as we go along. 1 second. So here are some useful integrals. First, the integral from 0 to pi of y times sine squared y dy is easy enough to work out. One uses separation of variables, and then and then it breaks down into problems that we've seen before. But this evaluates to pi squared over 4. Here's a rather similar integral from 0 to 2 pi of y times sine squared y dy, which is just pi squared. And then finally, this is one that's a little harder to work out. It's the integral from minus infinity to infinity of y squared times the Gaussian function, e to the minus y squared dy. And this is equal to to square root of pi over 2. All things that you can work out or look up, but we're just going to put those in the bank to use today. Okay, now let's talk about expectation values. So once again, quantum mechanics doesn't tell us the outcome of any individual measurement. It only lets us calculate the probability of obtaining certain specific results. However, we can use those probabilities to determine an expectation value. This is the average value that we would get if we did a large number of measurements on identically prepared systems. And we can just calculate that from the probabilities. So an expectation value is the average value of some measured property for a large number of measurements on an identically prepared systems. Okay, so to illustrate this, imagine a particle that's trapped in some bound system, like an infinite well, or perhaps an electron in an atom. Quantum mechanics doesn't tell us where the electron is at any moment in time. It only tells us the probability of finding it at a particular location. However, if we did a large number of measurements, we could and collected a large number of results, and we averaged those together, that would give us a value that we could compare to the calculated expectation value. Okay? Not sure if that was a perfectly clear result. But here, let's try to illustrate it with an example. Since we were just talking about this, let's illustrate it with the expectation value of position. Okay? And this is denoted this way. So we have our quantity, and then we put it inside of angled brackets to denote expectation value. It's like an average value. Here's how we would calculate this. The expectation value is just a weighted average of the possible positions. And we can get that from an integral over all possible positions of the position times the probability to find the system with the particle at that particular position. Okay? And of course, this is identically equal to the following. Okay? Actually, we can generalize this. The expectation value of any function of x can also be given this way. It's just the value of the function at any particular value of x times the probability of finding the system with a particle in that position, and then integrated over all possible positions. So, I hope the idea is clear. We can find the expectation value from a weighted average, weighted over all possible values according to the probability distribution predicted by quantum mechanics. Here, for example, let's look at this system, the particle in a box. There we are. Suppose the system is in its ground state, so that the probability density, yikes, the probability density looks like this. Okay, sort of like that. Okay, let's find the expectation value of the position for that system in that state. Okay. Now, I'm picking this because it's such a simple problem that I'm sure you can guess the answer right now, okay? But let's see if we do the math, if we get what we expected. So the expectation value of position should be the integral over all possible values of x times psi star psi dx. And then remembering what the wave function for a particle in this state is, we can rewrite the integral. So the wave function is that. And so the expectation value for position becomes the integral from 0 to L of this term squared times x. Because the wave function has this form inside of the well, but is 0 outside of the well. Okay? And to do this, we merely can substitute y for pi x over L, then dx is equal to L over pi dy, and we get the following. So we have 2 over L, and then dx is L over pi dy, and x is L over pi times y. So we get 2 factors of L over pi. Okay? And then we have the integral from 0 to the maximum value of y sine squared y dy. And then notice the maximum value. When x is equal to L, then y is equal to pi. Okay? Finally, notice that this is one of the integrals that I wrote down just a moment ago. Wasn't that clever of me? Here it is. So it evaluates to pi squared over 4. There we go. And canceling out the common factors, we get L over 2. So the expectation value of position in this system is L over 2. Are you surprised? Probably not, right? That's what we would have guessed. But it's nice to see the math work out. Okay, I'd like to do a second very similar example. 1 second. Okay, our next problem will be very similar, only now we're going to find the expectation value of the position for the n equals 2 state. Okay? And maybe you can guess this one too, or maybe not. Here, let's start by sketching in the probability density for the n equals 2 state of the particle in a box. There we go, more or less. Okay, Looks familiar. Well, let's go ahead and do this one as well. So now the expectation value of position is similarly the integral from 0 to L of x times the wave function squared for the n equals 2 state. And this can be written as 2 over L times the integral from 0 to L of x times sine squared 2 pi x over L dx. Okay? And now we just have to carry out this integral to solve the problem. And once again, we'll do a substitution to put this in a kind of general form. We'll let y equal, now it's going to equal 2 pi x over L. Again, it's the argument of the sine function, so that x is equal to L over 2 pi times y, and likewise dx is L over 2 pi dx. So with this substitution, our integral becomes 2 over L. Now we have a factor of x here and a factor of dx. So we get L over 2 pi squared, okay? And then we get the integral of y sine squared y dy. And now the integral runs from y equals 0 to the following. When x is equal to L, then y is clearly equal to 2 pi. So the upper limit is 2 pi. Okay? Perfect. And you'll remember that this is also one of the other integrals that we wrote down a few moments ago. Again, we can work this out by first doing integration by parts twice, and then by figuring out the integral of sine squared. But let's save ourselves a little time and see what this evaluates to. So it evaluates to pi squared, okay? So that our integral is then 2 over L squared over 4 pi squared times pi squared. And canceling out common factors, we get, of course, L over 2 once again. Okay, did you guess that one too? Maybe you did. I mean, the symmetry of the problem tells us something, doesn't it? Since this problem is symmetric about the center of the well, it seems like any average value has to also reflect that symmetry. But what's strange about it in this case is that while the average value is L over 2, the probability of getting that particular value when we do a measurement is 0. So that highlights something important. The expectation value is not always the most likely value. Instead, it's just the average that it's the average we would get if we did many measurements on identical systems. And so here, because the system is symmetric about the center of the well, we should get just as many results with a particle on this side as we do on that side. And so the average has to be L over 2. In fact, you can easily show that for any value of n, for energy states of an infinite well, the expectation value of position is L over 2.